Hello and welcome to the seventh lecture on coordination chemistry. We had in the last two classes, we have been dwelling on the geometrical and optical isomers, particularly stereoisomerism. We spent quite a lot of time. Now we will be starting, let me share my screen, we'll be starting a very important topic, that is the theories of metal ligand bonding. Yes. Hello and welcome to those who are watching in the YouTube. Today's program will be the beginning of a very important aspect of coordination chemistry is the theories of metal ligand bonding. We are joined by Silki, Ares, Krishna, Amlan, Udit, and others will follow. But if there are three theories, uh, the important for your examination is these are the two: VBT, the valence bond theory, and the crystal field theory, and the LFT or MOT, same thing, ligand field theory or molecular orbital theory. This we will be dealing here in some greater details to have an idea of how this is more beneficial than the other two. It takes the good aspects of both VBT and CFT. Some aspects are missing in VBT, some aspects are missing in CFT. Although CFT is more powerful than VBT, but LFT is the most powerful tool or theory to explain the metal ligand bonding. So today we shall be taking of valence bond theory. The assumptions are the metal ion, metal or metal ion, metal atom or metal ion uses vacant but hybrid orbitals to overlap. This is with the field non-bonding orbitals of ligands to form ligand to metal sigma dative bonds. or coordinate bonds or coordinate covalent bonds. The metal ion uses the empty orbitals but hybrid to describe the geometry. Depending on the coordination number, hybridization and shapes are different. Obviously, the ligand will act as, we have already said that ligand will act as the Lewis base, while the metal will act as Lewis acid. These things we have already done. Now, if you can make a table, if you have, because you have basic knowledge of hybridization, if the steric number is 2 or here the coordination number is 2, the hybridization is SP and the geometry or the shape is linear. Just we can give example, one example each. We'll get hundreds of examples. And if the coordination number is 3, then SP2, and it is trigonal planar or triangular. This you can have diamine silver plus. One example. Trigonal planar, we have, I will tell you some examples later. 4, there are 2 types of geometries and hybridizations. One is SP3, the usual one, tetrahedral, and we shortly write TD. There can be hundreds of examples. We shall be doing now. Be very, very same 4. There will be repetition, but this time DSP2 or it can be SP2D. We'll have square planar geometry and we call it SP, and there can be hundreds of examples. To name a few is tetracyanide-nickelate 2. Then we have 5 just for the faith. This is either DSP3 or SP3D. This is trigonal bipyramidal. You have pentacarbonyl iron 0 can be one of the examples of pentagonal. You can also have an alternative geometry, capped octahedral. I'm not writing those alternative geometry which are very uncommon. The most important is these two for you. 6 is either D2sp3 or sp3d2, and it is octahedral, and we write as OH. And there can be umpteen number of examples which we will be doing very soon. I am giving one example each. And there can be 7 D3sp3 or sp3d3. This is pentagonal bipyramidal. or capped octahedral and we will take many examples later. We can have 8 also, which cannot be explained by hybridization, square antiprism or trigonal dodecahedral, do dodecahedral or bicapped trigonal prismatic. So many possibilities are there. Will not bother our heads here. I will give you examples here. Here I can now give you hexacyanidomolybdate. Tell me what is the oxidation state of molybdenum?
+3.
Are you kidding me? Are you kidding me? Three minus plus three.
Yes, sir.
Yes, I'm sorry. So the plus 3 minus 6 is equal to minus 3. Yes, molybdate 3. So I will give you examples of others later, but let us plunge into the details of octahedral complexes. With coordination number 6, usually there is no other competitive geometry. Octahedral geometry is the first choice of coordination number 6. And there are two types, according to VBT, there are two types of octahedral complex. One is called inner orbital IOC. This can be also called low spin complex. Or sometimes it can be called spin paired complex. But the most popular is LS complex, low spin complex. The second category of octahedral complex is outer orbital complex. This is called high spin complex or HS complex. Some people also call it spin free. Spin free complex. Now, let me tell you a very important thing at this moment. The most important thing that we will be doing, we will be borrowing, Prabhat, a lot of ideas from CFT. VBT has no reasoning at all. Only plus point in it is shape, because hybridization will prove this shape, which can be confirmed by indirect methods. So the plus point of VBT is shape, but the intricacies, which one will be tetrahedral, which one will be square planar, which one will be inner orbital octahedral complex, which one will be outer orbital octahedral complex, that VBT can never ever tell. But since you are taking a course, I will give you a deeper insight. Even with the help of VBT, you can predict almost everything. Almost. Therefore, we start our program with inner orbital complex. Now, the first term is also a borrowed term. Strong field ligands, carbon donors, and nitrogen donors form this complex. You cannot ask me why. Why will come in CFT? Because we'll be applying in a very concrete manner to predict things. I'm telling you in advance. Strong field ligands, carbon donors, and nitrogen donors form the, this type of complex. These complexes, that is called inner orbital complex. And carbon donors are stronger than nitrogen donors. For example, if you put a little bit of example, you'll find carbon monoxide, carbon donor, cyanide ion, carbon donor, then ethylene diamine, nitrogen donor, but bidentate is stronger than monodentate. So this is a simple order. These are carbon donors and this is nitrogen donors. These are called strong field ligands, and these will form octahedral complex with inner orbital type. We'll see what is inner orbital type. In this, two inner n-1d orbitals, namely dx square minus y square and dz square, along with one ns and 3 np, px, py, and pz undergo D2sp3 hybridization. Hence the name inner, because the inner n-1 d orbitals are used because they are strong field ligands. They will try to cow down, chase the electrons in the inner d orbitals sometimes to get themselves paired so as to make low spin complexes. I will show you. Just wait. D2sp3 hybridization. If these two orbitals are occupied, fresh pairing occurs to in n-1d orbitals to create the two vacant orbitals. If these two orbitals are occupied, fresh pairing occurs in n-1d orbitals to create the two vacant orbitals. D1, D2, D3 metal ions have same number of unpaired electrons with both strong field and weak field ligands. So the term LS and HS complexes are not point to them. So the terms LS तो एबे पढ़ुचे एगुड़ा LS कहती कहबी काहेकि and or HS complexes are not applicable to them.
के ऊपर
Not are not sorry are not applicable to them. यार तुम्हें किंतु how you have missed out the direction today? You have been missing for the last 2 decades. Hello, Nihar,
Yes, sir.
and without any reason, without anything. Okay, let's continue. So D1, D2, D3 metal ions have same number of unpaired electrons with both strong field and weak field ligands. So the terms LS and HS complexes are not applicable to them. D7 metal ion gives LS complex with one unpaired electron in 5s n plus 1 s orbital. D8, D9, D10 metal ions form outer orbital complex, which we'll be studying in a bit. And the most important thing, due to internal pairing, of electrons in the inner n-1d orbitals. Hello and welcome. I could not publicize the conduct of the resumption of our coordination chemistry classes much. So, and also I didn't share with you, I forgot to share with you the YouTube link. Doesn't matter, this class is going to be a very, very useful class. And I will be putting all my experience in delivering this program. Due to internal pairing of electrons in inner n-d orbitals, the number of unpaired electrons get lowered. In D4 to D7 metal ions. Hence they are called low spin complex. Aguru LS mu lekhi sarchi kon low spin complex. Hello and Over?
Yes, sir.
Vinny cheese. Yes, Vinny. Vinny, someone. Yes, Vinny. Uh, Now, before we start, let me remind you that first row transition metal, scandium 21, this is 3D1 4s2, and scandium forms only 3 plus, doesn't form 2 plus. Transition metal chemistry is there. Krishna was, Krishna sent me the recent list of topics which have been deleted from the NEET as well as NCRT. So whatever Udit was saying, almost the same. So we'll be doing P block because we had only covered up to boron family, perhaps. Carbon, nitrogen, oxygen, halogens will be doing. Am I correct?
Sir, ଜମାରୁ ପଢେଇ ନଥିଲା।
Boron family?
No, sir, ପଢାଇନି। Sir, ଆପଣ କହିଥିଲେ କି 12th ରେ P block ପଢାଇଲା ବେଳେ ଏକାଥରେ ପଢେଇବେ।
Okay, we'll do that. Okay, welcome. Let me remind you, scandium is 3D0, 4s0. Scandium forms only 3 plus. This is scandium metal atom neutral. Titanium is 22, 3D2. And it can form plus 2 and plus 3. It can form plus 2 and plus 3. And also plus 4. Usually plus 3 and plus 4. If it is plus 4, if it is plus 3, then 3D1, 4s0. If it is plus 4, it is 3D0, 4s0. Plus 2 is very rare, but you can, if it is plus 2, it is 3D2, 4s0. Similarly, vanadium is 23, it is 3D3, 23, 3D3. And usually vanadium shows plus 3. If it is plus 3, then you know first electron goes from Ns, then N minus 1D. Then it will be 3D2, 4s0. And if it is plus 5, then it is 3D0, 4s0. If it, of course, plus 2, if it is 3D3, 4s0. Similarly, because you guys, you will be fumbling unless I remind you, chromium has a 3D5, 4s1. You know, there's a Hapfield stability factor that makes, and it shows plus 1 state. Plus 1 state will be 3D5, 4s0. Plus 2 is 3D4, 4s0. Plus 3 is 3D3, 4s0. Plus, and so on, continue up to plus 6. Hardly you will get complexes of plus 6. So we are going up to this. And then manganese is 25, is 3D5, 4s2, and start from plus 2, it is 3D5, 4s0, plus 3, 3D4, 4s0, and so on. It is plus 4, then 3D3. You can. And if it is iron, 3D6, 4s2, and plus 2 is 3D6, 4s0, plus 3 is 3D5, 4s0, and so on. Cobalt, 3D7, 4s2, cobalt, sorry, plus 2 is common, 3D6, sorry, 3D7, 4s0, and plus 3, 3D6, 4s0, like Fe3 plus. same is, no, Fe2 plus and CO3 plus have same electronic configuration, 3d6. And then nickel hardly shows states other than +2. So although it can go to +3, but the commonest is S2, this is 3d8, 4s2, 4s0, but many carbonyl complexes shows 0 state where it's both 3d8 and 4s2. And finally, copper is another transition metal in the 3D series. This is 3d10 4s1, the anomaly, full field anomaly. So in +1 state, it will be 3d10 4s0, and +2, it is 3d9 4s0. +3 is very uncommon, it's very strong oxidant. And finally, zinc, you will be having 3d10. It's not a true transition metal, shows only one oxidation state, that is 3d10 4s0, no other state. And let me tell you, the elder brothers here, molybdenum and tungsten, these are the 4d and 5d. Same electronic configuration, he says only one added. It will be 3d 4s, that will be, the 4d series will be 4d 5s, and the 6d series will be 5d 6s. This is 4d series, this is 5d series, and this is technetium is radioactive, rhenium. Forget about technetium. And iron, what? Ruthenium, rhodium. Uh, osmium. I am writing S plus. Cobalt, rhodium, iridium. I'm just writing X plus because there's so variable oxidation state, but only one step more. Nickel, palladium, platinum. And copper, silver, gold. And +3, it's shown. Silver is +3 is very difficult, but it can be possible. Zinc is only cadmium and mercury. Those have +2. Mercury can have +1 state. Okay. Then vanadium, niobium, tantalum, titanium, then zirconium, hafnium, scandium, yttrium, lanthanum. This is not very much required. So with this background, let us apply to a very simple compound to explain to you. This is hexacyanido ferret 2. And cyanide is a strong field ligand. I have already told you carbon donors and nitrogen donors are usually strong field donors. Carbon donors are stronger than nitrogen donors. So once you see cyanide or carbon monoxide, whatever, nitrogen, then you will be thinking that it is a strong field ligand, and the octahedral complex, the geometry is fixed. Unlike coordination number 4, which will have a different geometry, but here the geometry is octahedral. But their magnetic properties will change depending on whether it will be outer orbital or inner orbital. We are now studying inner orbital complex. Now, first what you do, iron 0, we have already written 3d6 4s2, and you find out the oxidation number in this complex, it is +2. So we write down Fe +2. Imagine that complexation has not happened. So it will be 3d6 4s0 as we have already listed. Then draw the box diagram. The 5 degenerate orbitals, you apply the Hund's rule, 1 1 1 1 1, then this 4s nothing. This is the state of uncomplexed metal ion. But the moment the ligands will approach and form a complex, and this is strong field ligands, these unpaired electrons, they will be sighing away to forcefully remain occupied as twins, as pairs, and give rooms. At least 2 rooms are required for the D2sp3 hybridization. Why dx square minus y square and dz square? It is because the lobes of dx square minus y square, they lie along the x-axis and y-axis. So also dz square, 2 lobes along z-axis, and the torus is lying along the xy plane, so that these 2d orbitals can mix well with the px, py, pz of the 3p and spherically symmetrical s. The hybridization will be effective if the 2d orbitals chosen are dx square minus y square and dz square. Now, these are all theory. There are 3 alternative theories. One will be having an advantage over the others. Every theory has its own uniqueness. And those theories have been accepted because their experimental determination of several properties, magnetic properties, color properties, spectra, all these have been corroborated by one theory or the other. I will tell you the pros and cons of each theory at the end. How CFT has more advantages over VBT, and what demerits are with VBT. All these things will be discussing. So before, and this is P3, they are also vacant. I told you that we need only vacant orbitals, and that to be hybridized. This 4p is vacant, 4s, 4p, and this unpaired electron which was there in the uncomplexed metal ion have to be paired in order to give 2 rooms vacant. So these 4 will be occupying in the 2 rooms. So there will be no unpaired electron left. And then you can use another color. If you have a red color pen, you put arrow mark, or else if you do not, then put cross marks. These are actually electron pairs. One is clockwise spin, the other is anti-clockwise spin. So this is D2sp3 hybridization will occur. They will belonging to a different categories of hybrid orbitals, which will be overlapping with the field lone pair orbitals of ligands, 6 ligands at the 6 directions of the octahedron. So you have to be really excited that whatever this theory says, same is the determination of magnetic properties. The number of unpaired electrons is equal to 0. It is diamagnetic in fact. Practically also this complex was found to be diamagnetic, so that the spin dipole moment, the magnetic dipole moment, spin magnetic dipole moment is 0. No unpaired electron, diamagnetic. This is because this is inner orbital complex. Pairing of inner d orbitals has happened, so that we don't find any unpaired electron left out to make it paramagnetic. On the other hand, the second example that we take is its sister ferricyanide. where iron is in the +3 state. This is ferri, or in the language of IUPAC hexacyanide, ferret 3. And directly I'm writing this is 4s 3d5 4s0. I'm not repeating the same, writing the metal atom first and then removing from the ns. As I have told you, for transition metals, ns and n-1d are practically the valence orbitals. Practically the n-1d takes part in bonding, that you can see now, that first electron goes from ns and then n-1d. So Fe3 plus will lose one more electron from Fe2 plus and it will be d5. So you draw the box diagram without complexation. According to Hund's rule, there are 5 unpaired electrons. 4s is 0, 4p nothing, px, py, pz, and this is 3d, this is Fe3 plus. But once there will be complexation with strong field ligands, immediately there will be pairing, as much pairing as possible. We need 2 rooms. So after pairing, we are still left out with unpaired electron, but our 2 rooms dx square minus y square and dz square, they are made vacant. Obviously, theoretically, they have to. If you are asked a question, which 2 rooms will be vacant? Obviously, the ones whose lobes are on the same plane or same line as the other s and p orbitals. S is spherically symmetric. It is mixable with all in all proportions. But this px, py, pz, they need lobes lying along the axis. Okay, then you can draw. These are the dative bonds. I'm putting crosses to indicate these are the lone pairs from the ligands. These are the electron pairs from ligands. The 6 ligands showing in a different sign, because we don't have much time to change the color. So I have put cross sign, cross sign to indicate the pair donated by the ligands, right? And you must mention here D2sp3 hybridization, so that the magnetic, it is paramagnetic, but contrary to what would have happened had there been no inner pairing, would have been giving a hugely paramagnetic substance containing 5 unpaired electrons, as you will find in FeH2O whole 6, which is an outer orbital complex, whose magnetic dipole moment is be as huge as 5 into 5 plus 2 square root Bm. But this actually practically gave a little dipole moment conforming to the presence of one unpaired electron. Number of unpaired electron, let us write down in short, UPE, unpaired electron number is equal to 1, not 5. So if somebody will ask you in examination, what will be the spin magnetic dipole moment of ferricyanide, you can find, you can do it by using the formula. So number of unpaired electron is 1 into 1 plus 2 root over. So this is root 3. Am I correct?
Yes.
1.732. Hello and welcome. Those who are watching from the YouTube, please uh, inform your friends if they are interested to immediately join. We are going to have fascinating discussion. Of course, those who will be missing out, those who have joined in Zoom but will miss out because of having some other assignment, can watch very meticulously after you get some free time and write down the notes. Now, I will give another example to show how, say, third example we will take Mn Cn whole 6 3 minus, where manganese is in the +3 state. Manganese, as you know, it is 25 3d5 4s2. And if you remove 3 electrons, then first this 2 and 1 from here, so Mn plus 3 is equal to 3d4 4s0, and then complexation will happen. But let's see what is the state of the uncomplexed metal ion. The Hund's rule will state that there are 4 unpaired electrons. This is 4s, this is 4p, this is 3d. But once you are complexing with strong field ligand, these unpaired electrons will be sighing away, सहम जाएंगे. सहमते वो pairing जितना जरूरी है, as much required to give 2 rooms vacant, उतना ही करेंगे, not more, not less. So when it forms a hexacyanide or manganate 3 complex, then only one pairing is required, because one vacant room is already there. So one and the other 2 will remain. If other 2 will be paired, it will violate the Pauli's exclusion principle, Hund's rule, because one room is vacant and you are pairing. It will violate Hund's rule. Therefore, only one pairing will occur, 2 unpaired electrons will be still there, and these 2 will be segregated, entering into a different family of hybrid orbitals. So we put cross sign for the donation from the ligand side. So it will be undergoing same D2sp3 hybridization, and it is paramagnetic, but you have to unpaired electron number is 2. Be very careful. This is important, as many guys will make the double pairing and make one room vacant, telling that it is diamagnetic. No, it is paramagnetic, having 2 unpaired electrons. Then I'll give another example to show where I have already told you for D1, D2, D3, doesn't matter whether it is cyanide ion or a weak ligands like aqua or fluoride, doesn't matter. I will give you an example. Chromium complex. This is a chromium is in the +3 state. So chromium as an atom, it is 3d5 4s1. And when you remove 3 electrons, it will become 3d3 4s0. And then there will be no necessity of any pairing that will occur here. Therefore, in the beginning, I have told that the high spin, low spin complex, that terms are not applicable in case of so the uncomplex metal ion is this. The complex ion is also the same, but excepting that 2 orbitals will be delinked from the unhybridized orbital and enter into a D2sp3 hybridization. These 3 will remain the same. No change in unpaired electron. For that reason, in the beginning, I have told for D1, D2, D3, low spin, all other cases that we have discussed, these are low spin complexes from D4 to D7 because the number of unpaired electrons get reduced while complexation with strong ligands happen. We'll see what happens to weak ligands. When one is weak, is unable to chase down the unpaired electrons to pair to remain together in one room. It's not possible by weak ligands. I am telling this with complete lending, borrowing of ideas from CFT so that even with VBT, you can answer questions up to magnetic properties, not color, of simple compounds, many complex which are complex, many complexes which are very complicated, which the magnetic properties can also not be explained by VBT. CFT is required. Sometimes MOT is required. Okay. But the only thing that we are left with is D7. D7, I'll be giving an example, COCN whole 6, 4 minus. I don't know which the number of example is 4 or 5, I don't know. The cobalt is an oxidation state of +2. +2 minus 6 is equal to -4. So when you write down cobalt 2 plus, it is 4s0 and this is 3d7, not 6. Cobalt 3 plus is 3d6. So when you draw the orbital filling diagram, Hond, and then poly, then you have left with 3 unpaired electrons, 4s and 4p are vacant, but we need, oh my God, this guy is really changing. Okay, 4s, 4p, then 3d. This is cobalt 2 plus, but once it complexes with strong field ligands, here there is a very typical thing that happens. Here 5s has to come into rescue. At least one pairing has to be done because we need 2 inner d orbitals free. So the other one has to jump to the next available less energy orbital. So after 4p, the n plus L rule, the Madelong's rule say that 5s comes. Many people write 4d. It's wrong. This is theoretically wrong because it's not filled. It is empty. So that 4p, after 4p comes 5. When it is already filled, then the screening effect will make it the opposite. But it's not filled, then 5s is less than 4d. So the electron will go to 5s and the sp3d2 hybridization will occur. This time I have changed the ink. There was no necessity for that. And the unpaired electron will be only 1, not 3. And it is paramagnetic, but weakly paramagnetic. And that will explain why cobalt 2 plus is a good reducing agent. It will be oxidized easily to cobalt 3 plus. By the loss of this higher energy orbital electron, this will be lost easily. So cobalt 2 plus is a good reducing agent to be oxidized easily to cobalt 3 plus. So otherwise, we'll talk about D8, D9, D10 in our outer orbital complex because they don't have any room. Two electrons cannot go to some higher place and you make the proof. It's not possible. So the outer D, ND, that will be coming into use. Now, I shall be doing a lot of exercises. But before that, let us write down outer orbital complexes, which are also called the high spin complexes, HS complexes, or spin free complexes, where nothing will happen. Here, uh, weak field ligands, the first important trick clue, form these complexes. Halogen donors like fluoride, bromide, chloride, and oxygen donor O donor like aqua, like uh, oxalato, like ACAC, acetonato. These are all oxygen donors. They are, and poorer is halogen. Among them, just like carbon donors were stronger than uh, nitrogen donors, here halide donors or halogen donors are weaker than oxygen donors. What does it mean? Weakness, strength, what does it mean? Everything will be crystal clear in crystal field theory. First crystal is literary, the second crystal is the name of the theory that we are going to study. So whenever you find any octahedral complex with coordination number 6, like aqua, fluorido, immediately you do not change the contour of the inner D. So in this case, NS, 1 NS, 3 NP, obviously PX, PY, and 2 ND, same x square minus y square and dz square. Outer ND, outer D orbitals undergo sp3d2. D2 will be written at the last because this indicates the outer D, not n minus 1d. That was 4s, 4p, and 3d. But here 4s, 4p, 4d. You might wonder why high pace is not taking place, because while it will occupy, since the theory says, since it will need 2 orbitals, so it cannot take high pace. It has to take D, which has 5 orbitals, out of which it will give 2 appropriate D orbitals that you know as hybridization. The inner n-1d orbitals remain intact, and hence the number of unpaired electrons remains unchanged. Whatever was there in the uncomplex ion, same will be the number of unpaired electrons even after complexation. The change that you notice there in in inner orbital complex, the low spin complex, particularly D4 to D7, such a thing will not be found. Number of unpaired electrons remain unchanged. Okay, if you have any one of you who are attending in Zoom, guys, I am not interacting with you because I know for sure that you guys are understanding. Otherwise, I would have chatted with you and I would have taken some extra effort to drag you into focus because I know that you are in focus. That is why. And if you have any other assignment, you can leave the class and you can definitely see, because it is 6 o'clock, we'll have another half an hour program before we close. Uh, so that is why, so they are called HS complex, high spin complex, because the number of unpaired electrons become high, remain the same, the magnetic moment becomes higher, so they're uncommon. And so uh, supposing we take FeF6 3 minus, where iron is in the +3 state, hexafluoridoferrate 3, or you can call hexafluoroferrate 3. So Fe3 plus is 3d5 4s0, 3d6 4s2 is iron, Fe2 plus is 3d6, Fe3 plus is 3d5. But see, and here you have to consume a lot of space. This guy is creating problem. Who are you? PDF suit. Get lost. That's not going. So you have to draw 4s, 4p vacant, 4d also vacant. Now they will be used up 5 orbitals. And this 3d, according to Hund's rule, there are 5 unpaired electrons in Fe3 plus before complexation. After complexation with a weak ligand, because fluoride, bromide, iodide, aqua, these are all weak ligands. Uh, then there will be nothing. Nothing will happen here. Nothing will happen here, no change. But cross, 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 cross will happen now. This is sp3d2, the same dx square minus y square and dz square. So the number of unpaired electrons remains the same and highly paramagnetic, high spin complex. You compare with ferricyanide. You compare with ferricyanide ion, because it was forming inner orbital complex, pairing was happening, same +3 state, you find the number of unpaired electron was 1, because it was inner orbital complex. But chloride ion is a weak ligand. The moment you see there is a weak ligand, even I can give you another example where hexaqua cobalt 2 plus, aqua is also an oxygen donor. Cobalt 2 plus is the D7 4s0 configuration, and nothing will happen. So please allow me to to avoid doing the picture second time, to save time. So I'm writing down the complex in one go without writing the uncomplexed ion, because nothing will happen. Hund, hund, on the 7 electrons, hund, 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 then poly, poly. 3 unpaired electrons will remain, no pairing, nothing. But had it been cyanide ion, then you remember one unpaired electron was being promoted to 5s. We were keeping it 5s, but some authors they say 4d, but I beg to differ. and I am in opinion with many other authors of the Western countries that it remains in 5s. You know, uh, that that happens, and that the unpaired electron number is reduced from 3 to 1. But here it will be 3, and this is 4s, 4p, 4d. This is 3d. 3d will be untouched. So unpaired electron is 3. So up to d4 to d7 with weak field ligand, strong field ligand, the character will be completely different. The magnetic property will be completely different. But d, for example, I will make a complex NiCN whole 6, 4 minus. So there is no way out. Even if it is a strong field ligand, it cannot chase away uh, 2 electrons to keep it in the higher cells, and that energetically is unfavorable. And also experimentally it has been proved that it contains 2 unpaired electrons, whether it is strong field or weak field. It has to go for outer orbital complex. This is nickel, is in the +2 state. This is 3d8 4s0. There is no way out for 7. Only 1 electron needs the jumping, but here there are 2 electrons. This is 3d8 4s 4p 4d, and hund poly poly poly. So there is no room. If you, oh well, if the coordination would have been 5, then 1 room would have been required. I will tell you, DsP3 hybridization with a strong ligand. Of course, with a strong ligand. Cyanide is a strong ligand, but that won't happen here. Geometry is octahedral, but most important is to predict the number of unpaired electrons. So this will be remaining as such. So I would like you, have you written down?
Yes, sir.
I would like you to take down uh, D8, D9, D10 metal ions give only outer orbital complexes and also give same number of unpaired electrons with all types of ligands, strong field or weak field. So we have these ones you have to do. Uh, uh, I will give you the file. You have to do. I say out of that, let me take out a few. Let me take out a few for our analysis. You have to tell me, this is SAQ. You have to tell me what is the oxidation state of the metal, and also tell me that whether it is will be IOC, or if it is between D4 to D7, then the question of HS or LS will come. But this is surprisingly D0. Sorry, oxidation state is 0. And of course it is 4s1 and 3d5. Chromium is in the 0 state. This is hexacarbonyl chromium 0, a neutral complex. So chromium 0 is 4s1, 3d5, 4s1. So it is very typical. You know, carbon monoxide is one of the strongest ligands, carbon donor, very strong. We shall, in the CFT, we shall know a series, just like you studied the electrochemical series to grade the different half cells, uh, electrodes in the decreasing order of SRP, standard reduction potential. In the similar manner, you will have a long series in which all the ligands will be arranged in the order of their strength. That strength is their octahedral splitting. That is experimentally determined from the absorption spectrum. We'll be doing a lot of calculations. And also in the tetrahedral and square planar complex, their values, the corresponding values, delta values. So this chromium.
So diamagnetic.
Oh my God, Krishna, you are really wonderful. Now, according to Hund's rule, there are 6 unpaired electrons, 5 in the 3D and 1 in the 4s for neutral copper atom. But since carbon monoxide is a Hiromarka, the most Hiromarka ligand, like all of you, and like I don't sell, it will definitely try to pair them as much as possible, as much. So once it is complexed with Hiromarka, so pairing will occur, and this is 4p, this is 4s, this is 3d, and there will be pairing this 5, and this one is also will be included. Altogether 6 will be paired in the 5 rooms, and 2 rooms are available. See the beauty of the theories, how the theory predicted is telling, matching with the actual experimental finding. Hexacarbonyl chromium 0 is a diamagnetic complex. So there lies the success story of the theory. This is D2sp3. And same, another example I'm giving, CONO2 whole 6, 3 minus. This, along with potassium ion as its counter ion, will give a yellow precipitate when you test for potassium or cobalt. That you will study in analytical chemistry, salt analysis. This is what common people call cobaltinitrite ion, but it is hexanitrite N cobalted 3. So cobalt. So tell me whether it is IOC or LOC, OOC. Nitrogen donor is a strong donor. It is not ONO. ONO is a weak donor, that is oxygen donor. Nitro is a strong donor because N is the donor. I have already told you that nitrogen donors and carbon donors are strong field ligands. So first of all, you decide that it has to be a IOC, inner orbital complex, where pairing might occur. This is +3. So same thing will happen. This is D6. This is D6, 4s0. D7 would have been cobalt 2 plus, cobalt 3 plus is this. Then pairing will occur. It is a diamagnetic. Immediately we'll say the complex is diamagnetic. So in the uncomplexed ion, there are 4 unpaired electrons. But once it is complexed with a strong field ligand, this will be paired. So fortunately, there will be no left out electrons in the d orbitals. So it will make the complex completely diamagnetic, which are repelled by a strong external magnet. The property of diamagnetic materials, they are repelled by an external magnetic field, while paramagnetic substances are weakly attracted by an external magnetic field. And I have given so many examples for you to decide. If there are some exceptions at this moment, you will be not be able to judge what will be the nature of the octahedral complex, whether IOC or OOC. These red ones you don't attempt, because they need a little more knowledge of CFT. Just I can sound you, if you will not be feeling suffocated, that then I can sound you in advance that just like students becoming hero marka, like ligands are strong filled and weak filled. Similarly, the metal ions also can be strong filled metal ions, weak filled metal ions. So, in presence of weak filled metal ions, which are usually in the lower oxidation state of manganese and iron, even to some extent cobalt, 2 plus state, even the borderline ligands. Aqua is the borderline ligands from the weak category, is very close to the strong, and ammonia is a borderline ligand in the side of the strong. So with weak field ligands, when the teacher is weak, then if the students are strong, then it becomes something different. So with Fe2 plus, Mn2 plus, even ammonia will not give inner orbital complex. The inner d orbitals will remain intact while the outer orbitals will be used. This will have a strong bearing on our analysis of tetrahedral and square planar complexes. Here it will be of less importance, but it's important. Here chromium, although it is a strong field ligand, let me tell you in advance that it will form outer orbital complex, because chromium 2 plus is a very weak field metal ion. Similarly, aqua being a, oh, of course, no, sorry. Amine, same thing happens here. Amine being a strong field ligand, usually with ferrous ion, it will form outer orbital complex. Manganese 2 plus, same is the situation, outer orbital complex. Even water being a weak field ligand in the category of oxygen donor, but cobalt 3 plus ion is a very strong teacher, like your teacher. Oh, I'm sorry. Self-aggrandizement is not good. Cobalt 3 plus is a very strong field metal ion. It has got also an order, spectrochemical series of metal ions. It is very high in the hierarchy. So the borderline ligand aqua will behave as a strong field ligand, and its reason we can explore in the CFT, and this will form inner orbital complex, right? So these things you have to, I have written for your, I mean, getting a little bit of help, I have written in between brackets the number of unpaired electrons. You have to draw this diagram in every case, and so that the number of unpaired electrons matches the one which I have given. You will definitely answer everything, excepting these four, which are also, after having told you the secret, you can also do IOC, OOC in these cases. So with this, we close today's session. This one, we have aqua ligand, we have done already, where outer orbital complex we have done, this we have done, everything we have done. This also you, one we have done, cobalt 3 plus, cobalt 2 plus, same. Nitro is such a powerful ligand, the number of unpaired electrons will be different. It was 5, it was 6, having completely diamagnetic, but this will be 7. Cobalt 2 plus is D7. There will be one unpaired electron left out, but still it is a IOC. Platinum, we'll talk about this. I have deliberately written it is diamagnetic. if you consider chloride ion to be a weak field ligand, this is an exceptional case. I will tell you the reason later, not later, tomorrow. Okay. Platinum is the sister, this is of course platinum 4 plus. You are lucky, not platinum 2 plus. Platinum 4 plus is 6s0 5d6. So they will internally, just like any d, 3d6, 4d6, they will internally, they will pair and produce diamagnetic d2sp3 hybridization. I was really mistaken for platinum 2 plus, where platinum 2 plus octahedral complexes are very rare, but we will talk about that little later when we talk about the tetrahedral complex vis-a-vis square planar complex in coordination number 4. So this one is easy because it becomes 5d6, 6s0, 5d6, because platinum is in the +4 state. So in this way, you complete up to this. I had in mind to cover both coordination number 4 tetrahedral as well as square planar today, but it could not happen. Doesn't matter. It's very, once you understand this, then extending this to CFT will be your baएं हाथ का खेल, is your left hand's job. Just the concept is different. Here it is covalent bond, there ionic bond. Surprisingly ionic bond. That is the only demerit, that CFT will not talk about geometry, shape. It will talk about everything else. Color, magnetic property, everything else. Spectrochemical series, absorption spectrum, everything. Uh, Thank you, Toka Maika. That Toka Maika is watching from YouTube and he is writing, you are doing an amazing job. Thank you. In my own little way, uh, instead of, at this age, instead of lying down and counting days, if I spend time with the young students like you, young friends like you, it will be my pleasure. Thank you, Toka. So this ends today's class, and tomorrow at the same time, make sure that you tell others who have, those who are watching in YouTube, who have not watched, because I could not publicize this link. Ask them to watch this before watching the tetrahedral and square planar complexes. Immediately we will follow CFT. Things will be easier and easier. Bye-bye. Hello.
Thank you, sir.
Hello.
Sir.